Hello everyone and welcome to today's video where we will be jumping into the topic of sensors and instruments from the instrumentation ATPL subject. It's a really interesting one. It blends a little bit of HK as well as the advanced instruments and practical real-life scenarios in order to ask us some questions. So I'll try to give you some explanations as well as show some extra graphics and materials that will for sure help you in understanding all of these a little bit better. So without any further ado, let's jump into question number 1. And all of the 6 ones that you'll see have actually appeared in the last 30 days across all EASA authorities in real-life ATPL exams. So for question number 1, the front probe of an EPR system becomes blocked during takeoff due to debris, ingestion, or icing. The EPR gauge will indicate. Now, the EPR is the engine pressure ratio. Generally speaking, some of the modern jets use EPRs in order for us, as pilots, to manage the thrust. Some of the newer jets today will use N1, however, the EPR sensors are still there because all these calculations are still given to the FADEC in order to understand what is happening inside the engine. By definition, the EPR will be our pressure going out divided by the pressure going in. And generally speaking, this is the primary means of managing our engine's thrust. Now, as you can probably imagine, as you are speeding up or adding more power to your engine, of course the pressure increases at the outlet because we're adding more fuel. However, because of the ram effect, the air is also stopped at the nacelle of the engine, so the pressure slightly increases as well. This is why it's very important that this EPR is always positive, as it should be in all normal operations. However, there have been instances when, due to debris or even icing, the EPR probes on an engines become blocked at the front. In that case, as you can imagine, the pressure in the back continuously rises, so the out continuously rises, while the in, which is our divided by, it will stay relatively constant. In that case, the EPR will start to rise artificially, even though it doesn't represent the true rise in the EPR. This is why this can give us a false higher than the actual value of the EPR, and this is also when it's a good idea to start monitoring the N1, which can give us the appropriate overview of what's happening in the engine. I also wanted to show you, so this is a military aircraft, however the engine is an IAE engine. This is exactly the same one that is used on some of the A320s and Airbus's A320 ones. And you can hear there is a little probe at the very front here, and you can see it if you are boarding an aircraft in real life as well on most of the Airbus aircraft, and you'll see that this is actually the EPR sensor that we are discussing right now. There is a very, very similar one at the back of the engine, measuring the EPR by dividing the out by the inlet pressure. And now going into question number 2. So what should a flight crew do following the loss of all fuel indications? So this is something that might seem relatively scary at first. However, remember that fuel indications do not mean loss of fuel. And this is a very important thing to remember. Generally speaking, if you lose all fuel indications, it is not entirely safe to continue the flight. However, it is not any type of imminent or immediate danger. That is why we should always, as pilots, not rush into any decisions. There are some mental models and frameworks that we should follow in order to make the decision. However, first thing that you should remember is to always follow the checklist and your standard operating procedures. Do not try to come up with these procedures on your own. There are very, very smart engineers that are behind these, and this is what we should do. And I will show you one in just a second. So going through the questions, pull and reset the circuit breakers to check if the system reset restarts, unless the checklists say otherwise. I would always go for an answer that includes a checklist, and this is what you should always do, no matter what is happening. Land as soon as possible and prepare for power of landing. If only the fuel indications are lost, your main threat will be missing a fuel leak. However, these two things happening at once are very unlikely. Open the crossfeed valve to make sure the plane stays in balance. Generally speaking, no. Generally, the plane will stay in balance anyway, unless there's a problem with one of the fuel lines. And turning off all fuel pumps for 10 minutes makes absolutely no sense. You would still be able to fly with gravity feeding. However, this includes another separate row of events and checklists that you need to take into account. And generally speaking, I wouldn't consider entirely safe. So of course, pulling and resetting the circuit breakers will be the correct course of action. I have here a quick reference handbook actually for an Airbus type aircraft from A318 to A321. And you can see for the fuel part right here, this is our system reset for loss of fuel quantity indication or simultaneous triggering of the following things. And you can see on the ground or in flight, the action made by the pilots is to pull the 3 circuit breakers on all these panels and then wait 5 seconds before pushing them in, making essentially a successful system reset, in which case the fuel quantity indication will be re-established within 1 minute ideally. Of course, if it's not reestablished, then you can go forward with your decision-making process and decide whether it is safe to continue to your destination or maybe divert or return to your departure airport. However, that is all after you made a successful or unsuccessful system reset. And now going into question number 3. So the hydraulic pressure is sensed by. And now this is a question that also blends a little bit from the basic instrumentation, and of course the hydraulic pressure will be sensed primarily by a Bourdon tube. And I have a couple graphics that I wanted to show you from one of our previous presentations on instrumentation, where we went through 4 of the most common pressure sensing instruments in an aircraft. For the exams, you will need to remember the aneroid capsule, which is for low pressure and easily readable systems. So most cases this will be your pitot-static system. Then you have also bellows, not good for high pressure, but it's quite sensitive. Bellows can be used in, for example, also some of the basic instruments from the basic 6 or your 6-pack, such as the airspeed indicator. And then we also have diaphragms, which will be for higher operating ranges. However, the sensitivity will reduce greatly at higher pressures, and they will be mainly for controllers that will control the successful work of other instruments. And lastly, we have the Bourdon tube, which is the sturdiest of the 4, which will be used for the highest pressures in an aircraft, such as hydraulic pressures. So remember that hydraulic pressure will be around 3000 psi in some airliners. In some bigger ones, it can be even more, up to 5000 psi in, for example, the A380. So these pressures are great and enormous, and this is where the Bourdon tube usually comes into place. And now going to question number 4. So during takeoff, the EPR indication of an engine drops unexpectedly. What is the correct course of action? So again, going into the previous question, we already know what the EPR is, the engine pressure ratio, so the ratio between the pressure going in and the pressure going out. Now, if you lose the EPR indication of an engine, there are 2 things that essentially could have happened. Thing number 1 is that the sensor has failed, or the circuits have failed sensor-wise, or 2, you actually lost your engine power and generally your engine. And this is the first thing that you should do before making a very important decision, whether you will continue without an engine or whether you do have that engine. So first thing you do once you lose your EPR indication, you need to cross-check it with something else. And of course, the correct course of action here will be to confirm the status of N1 and continue the takeoff, N1 being your low pressure RPM, which is shown in the percentage of our maximum design RPM of the spool. So of course, we do this to make sure that this is a sensor failure rather than an engine failure. A second consideration here, which of course will be besides this question, because I know many people like to consider the cancel the takeoff answer here. Remember that there is also a concept of high and low speed regime. I believe for Boeing aircraft it is 80 knots. For the Airbus aircraft, the cutoff line is 100 knots. So this is irrespective of your V1, which is the decision speed. So for some of the failures, we will stop no matter what below this high speed regime mark. So 100 knots for Airbus, 80 for Boeing. However, above that, most cases will continue the takeoff unless the aircraft is not safe to fly, there is a fire, obstruction on the runway, or or the aircraft is essentially unable to continue the flight. However, if we have an EPR indication above 100 knots and we can cross-check that this is just a sensor issue, we will usually take the aircraft into the air. Below the high-speed regime mark, I could justify the answer to cancel the takeoff. However, the examiners want you to select the option of confirming the status of the N1, meaning whether the engine actually works or if it is a sensor issue. For question number 5, which of these statements about fuel quantity measurement are correct or incorrect? The quantity of fuel can be measured by volume. So, of course, volume, this happens very often. So, for example, in some smaller aircraft, you can have the fuel quantity measured by volume in, for example, gallons or liters, very common in general aviation. And however, in the bigger jets, most likely you will have the fuel measured in mass. In most cases, it will be kilograms or pounds. This is absolutely a normal thing to do. GA will usually use liters or gallons. The commercial aviation will most likely use kilograms and pounds. It is also very important that once you receive your fuel slip from the handling agents, it needs to show you the fuel density, because this is then used for our aircraft to make sure that it calculates the appropriate values of fuel usage, and for us to decide and know how much fuel we actually have and we are using. So this is something that needs to be accounted for, especially when the fuel is given by measure of mass. However, both are correct, and you can see both depending on the aircraft type. And now going into the last question, so the question number 6. In a turbine engine, what is the parameter N1 which is used to represent thrust? So of course, we already mentioned it, and that the N1 is the low speed spool, the low pressure compressor speed, which is showcased as the percentage of maximum design RPM for our engine. And of course, N2, on the other hand, will be the rotational speed of the high-speed spool. And I can show you an image right here. This is, of course, a simplification. However, the N1 is this blue spool, which also will represent the speed of the fan at the front of the aircraft. And N2 will be our high-speed spool right here. However, the N1 is a good representation of the air mass and the mass flow of the air that is going through the engine. And this also represents very well the thrust that we are actually achieving with our engine or with our with our aircraft. And this will be everything for today. Thank you so much for watching and tuning in. I hope this was helpful. I wish you all the best with your instruments exams, and I hope to see you in the next video. Bye-bye.